Let us recall our discussion last time. So we introduced the concepts for building images uh, with the presence of mirrors. So we considered flat mirror and also um, spherical mirrors. So in particular, reflection from the inner part of a spherical mirror. We have several parameters which are important for us. First of all, if we consider spherical mirror, that is radius of the circle of the curvature of this mirror, then that's distance from the object to the mirror, and also we care about distance from the mirror to the image. Who will recall how we distinguish between imaginary and real images?
Reflect rays pass through the image. The
So if reflected rays pass through the image, then we have which one? Real. If we need to extrapolate reflected rays in order to get the image, to see this point of conversion or extrapolated reflected rays, we deal with imaginary image. So what do we need to build the image? We need at least two rays. So as shown here with red and blue, um, they need to hit the surface of the mirror at different angles. So we have different options. For instance, here it goes through the center red, so it hits at right angle, so it comes back at the same direction. And another hits at some angle theta. So this we may have more rays to be considered, but two is the minimum, and that allows us to get the image. Also, image could be either in the same orientation as object, or it can be flipped. So in that case, we need to remember when we have this modification, we have sign minus, which tells us that the object is flipped over, like shown on this figure. We finished our discussion with the mirror equation. Let us write it down. So let me come back to. So mirror equation was derived as follows: 1 over P plus 1 over Q, and that was equal to 2 over R. So now let us consider that an object is placed at a very big distance from the mirror. So in that case, P, which defines as the distance from the object to the mirror, will approach infinity. If it's approaching infinity, then Q, we can rewrite this equation: 1 over Q will be equal to 2 over R. And here we can introduce an important parameter, which is focal distance. F will be equal to R over 2. So this is the expression for focal distance of a spherical mirror. So it's twice smaller than the radius of the curvature. Now, if we come back to the slide, so this is the scenario when object is located very far from the mirror. So in that case, all rays which are coming, like reflected or originate from the object, they are traveling parallel to the optical axis, like prime optical axis, principal optical axis of the mirror. And in this case, when they hit the inner part of the curved mirror or spherical mirror, they will be all reflected in a single point, which is located on this principal optical axis, and its position, its focal distance, is half of the radius. Uh, so if we have now the different opportunities for choosing rays, we need to remember how they will behave. So one option, if we consider some ray which hits the inner part of the spherical mirror, uh, being parallel to the principal optical axis, like the reflected ray will go through the focal point. So if uh, the incident ray goes through the central point of the curvature, then it will just come back through the central point to the point where it was originated. And obviously, if we place our object in the focal point of the mirror, then all rays which will hit the mirror will be reflected parallel to the principal axis. So, for instance, if we consider some projector to get some illumination at long distance, we want to place a bright source of light in the focal position of the mirror, and then it will be projected to large distance with very small angle of deviation from this optical axis.
So we're maximizing it. Yes.
Well, if your goal is to have a beam of light traveling like large distances without large dissipation, like increase of the angular size, then this is the way to go. So definitely not always that's the case. For instance, here we also have light sources, these lamps, and the goal is not to create a very small area, illuminated area. We want to illuminate whole area of the room. That's why we don't have any like mirrors to concentrate this light in a narrow slit. We have in contrary this rough, like uh, not transparent rough glass or plastic surface which actually scatters the light in different directions, and that allows us to get more or less uniform illumination of whole room. So that was about inner part, but also we can shine light on spherical mirrors using its outer surface. And in this case, we follow the same procedure. We consider two rays. So one ray hits the surface at right angle, so it comes back to the point where the ray was originated. Another goes with like parallel to the principal optical axis, and reflected ray, when we extrapolate it, it goes through the focal point of the mirror, so it works in both directions. It's just the fact that when we shine light from the outer side, obviously the reflected ray doesn't go itself through the focal point, but if we extrapolate reflected light, then this line, extrapolation line, will actually go through the focal point. So here we see that technically these reflected rays do not intercept, so we deal with imaginary image, and we need to extrapolate both reflected rays and find the interception point. So here we end up with um, uh, upward, so it's not, the image is not flipped, but imaginary image with some distance q from the mirror. So these are the main aspects of building image taking into account reflection from inner and outer side of spherical mirrors. And obviously, this is not like mirrors is not the only option to be integrated into some optical systems which allow us to create images of different objects. So if we deal here with reflection, there is another opportunity is refraction. So we also need to know how we can use such phenomena as refraction of incident rays in order to build some images. So tell me, what do you know about refraction? Huh? When do we have this, observe this phenomenon, refraction? Can we have any refraction if we deal with a mirror?
So
Why no?
because like totally reflective. Yeah.
So we consider that mirror is uh, providing us with 100% reflection coefficient, which is close to true. So if, by the way, any ideas how usually mirrors are fabricated?
They're like maybe some metal, like silver.
Mhm.
Very thin layer of silver is attached to the glass.
So it's usually deposited on glass as a thin film with some vacuum deposition. And probably you may have some protective coating in order not to scratch the silver coating. Um, Usually it's actually aluminum, it's cheaper than silver. However, silver probably would work better in the visible spectral range. If we deal with infrared light, then we want to use gold instead of silver or aluminum because it reflects much better in the IR region. Uh, and if we assume that the film is thin, it's let's say thin, like thick enough that it doesn't allow light to go through it, so it should be 100 nanometers and more. In that case, we do not observe any refraction. However, if we're talking about refraction, so in this case, we need to have an interface between two optically transparent materials. That's important. We cannot have one transparent and another not transparent because then this refracted rays will be absorbed in not transparent material and we will not get any image. So they will be just absorbed inside this material. So both materials should be transparent in given spectral range where we use these instruments. However, they need to possess different refractive indexes. This N1 and 2. If they are the same, so it could be, it's kind of difficult to create such conditions, but we may have different materials, but they possess the same or let's say very close values for refractive index N1 and N2. And regardless the fact that these are different materials, in like from optical point of view, this interface which exists technically, there is like interface between two materials, but from optical point of view, this interface will not be there and nothing will actually happen. So when we have this refraction, do we have any reflection? So you told me that in case of reflection, in case of mirrors, um, we don't have any refraction. So everything is reflected. What do you think about this scenario? There is the concept of total reflection, but not refraction.
But it absorbs some maybe parts of light, but most of it goes through.
Well, not necessary. So that's actually one of the problems of instruments with lenses. So obviously, uh, lens is an optical instrument which forms image via refraction. However, since we have this difference in refractive indexes n1 and n2, we obviously have some reflection. So previously, if we had reflection from a mirror, light intensity more or less was the same. It was not reducing because all light was reflected. However, here, regardless of the fact that this material also transparent, part of this is not shown on this image, but you need to understand that if we have an interface between two materials with different refractive indexes, part of this light will be reflected. So we will lose part of the light intensity, and then the rest, which actually managed to penetrate, be refracted, will form the image. So if we have very bright conditions, that is not a big problem because we have still enough light penetrating into the second medium and forming this image. However, if we are observing some dim objects on the maybe bright background, that could be already a challenge because we lose part of the light, but via reflection, and this should be taken into account because there are options to create some anti-reflection coatings, and they are very widely used in all modern optical systems which are working with lenses. So surface of lenses is covered by these anti-reflective coatings. We will consider them during topic interference because they are based on the interference. Their operation is based on interference effect. However, at this point, I think it matters to highlight this factor that a part of the light will always be reflected. So now we see that after refraction, this angle changes of the rays traveling, they will intercept in a point which also gives us the image. In this case, we have a point uh, object, point image. They all intercept, so this will be the real image of the object, and we also deal with the distance from the object to the surface of the interface, from the surface of the interface to the image. And another important parameter is that radius of the curvature of this interface between, um, let's say, air and glass, if we consider some classical example. This is so far not a classical lens. We will deal with it a little bit later when we consider real lens. But this interface between air, let's say, and glass, is already enough with some curvature to form optical images. So now let us consider in more details, more quantitative approach, what actually happening. So we have some ray originated from the object at distance.
Sorry, sir.
Yes.
Image means the concentration of light in one place. Yeah.
Well, that is focus of light. So the thing is that if we consider some previous examples, because here it looks like we concentrate this light which originates from the object. However, it's not true that we get concentration of light, because concentration of light would happen when we have infinitely far source of light, then all beam like rays which originate from this source will go parallel to the principal optical axis, and then they all will be reflected and will get into one point. So means that all rays from the whole object will be concentrated in one point. When we form image, what we here, we just pick up a single point of an object, and then we make sure that all rays which originate from this single point, which represent a tiny part of the object, will actually intercept in a given point. Or the extrapolations of reflected light, for instance, will intercept in this given point. So that is true for very small part of extended object. However, if we pick up another point of this extended object, then it will not, the rays originated from this point will not be intercepted in the same point of image location as those originated from the previous point. So it will be another point because we have, since we have extended object, we should also have extended image. So that's why we cannot say that we concentrate light. But if we divide like extended object into point light sources or reflecting light points, then all rays which originate from these points will intercept in a given point. But if we move to another point on the object, then these rays will be intercepting in another point of the object, of the image. So we have extended object, we get extended image. Only in the case when extended object is very far away, we will get image of this extended object located very far away as a point in the focal at the focal distance from the mirror. In that case, we can claim that we concentrate rays originated from any point of the object in one point of the focal image. So for instance, if you take magnifying glass and align it with sun, so you can, sun is a huge extended object. However, regardless of the fact that it's huge, it's so far from us that we consider it as a source of light which is infinitely far away from the lens. So in that case, you have parallel rays which you can concentrate in a single focal point and do some damage to your burning surface. So be careful with that. So if we consider this scenario, we have some ray originated from an object, then it hits the surface of this interface between first and second medium at some angle θ1. This is perpendicular, right, normal to the surface in given point P where the incident ray hits the interface. Then because of refraction, this angle will change when the ray is refracted and goes inside the second medium. So it will be some θ2. And then it will eventually come to the image point. So as you remember, we discussed this when we considered law of refraction. We discussed the relationship between incident angle, refraction angle, and refractive indexes of first and second medium. So let me come back to whiteboard and we write this down. Yeah, maybe before we proceed further with another equations. So here, when we introduce the focal distance, we can rewrite the mirror equation as 1 over p plus 1 over q, and that will be equal 1 over focal distance. So that's also a quite commonly used equation when focal distance is equal to half of the radius of the curvature of the mirror.
So now let us write down this refraction equation, that is n1 times sinus theta 1 is equal to n2 times sinus theta 2. So now, if we consider a very small incident angle, so theta 1 is small, then obviously theta 2 will be also small. So we can write that sinus theta 1 is approximately equal to theta 1. Sinus theta 2 will be also approximately equal to theta 2. So we can rewrite this in the following way. n1 times theta 1 should be equal to n2 times sinus by theta 2. So that's a simplified case when we consider small incident angle. And now what we want to do, let us come back again to the slide.
We want to represent these angles theta 1 and theta 2 in terms of other angles, alpha, beta, and gamma. So how we do this? We consider two triangulars.
So let me show them here. So it will be first triangular point O, P, and C. So let's look here. We have angle alpha, angle beta. They are internal angles of this triangular. So this external adjacent angle, which is theta 1, this will be theta 1 is equal to alpha plus beta. So now let me delete this. We will consider another triangle. So it will be PIC. So the same story, we have that theta 2 gamma, and beta can be expressed as the sum of theta 2 plus gamma. So we can now express theta 2 from this second equation and substitute it in the refraction equation. So let us come back to the whiteboard. So we write here that theta 1 is equal to alpha plus beta, and beta is equal to theta 2 plus, what was that? Gamma, yes. So now we substitute, like express theta 1 and theta 2 in terms of alpha, beta, and gamma. So we will get the following. It will be n1 times alpha plus n2 times gamma, and that is equal to n2 minus n1 times beta. So now we don't have theta 1 and theta 2. We deal with alpha, gamma, and beta. So why do we want this? Because of the following reason. So let's again look at our figure. So now,
when we operate with these angles, we can represent them with these distances. Distance from the object to the interface, also distance from the interface to the image, and also here is our radius of the curvature. So how we do this? So this is the distance from the prime optical axis to the point where the incident ray hits the surface of this interface. So we can write that tangent of this angle alpha will be equal to the ratio of this d divided by p. So there is some gap between p and actually location of this perpendicular d. However, if we consider initial condition, we assume that theta is very small. So if theta is very small, then it should be close to the surface, to this extreme point of the surface, and then this gap will be negligible. And so on we can do for all other angles. And assuming that angles are small because theta 1 is small, it means that all these angles are small. We can, in first approximation, represent this tangent alpha as just alpha. And that will be quite accurate, assuming that theta 1 is very small. So let us do this.
Very and flat.
Yeah, so if angle is small, then sinus theta and tangent theta we can represent just as a theta with quite high accuracy. So we can write that tangent theta, no, sorry, not theta, but alpha, approximately equal to alpha, and that will be equal to d over p. Then tangent beta will be again approximately equal to beta, and that will be equal to d over r. And tangent gamma approximately equal to gamma, and that is equal to d over q. So now, when we substitute instead of alpha, gamma, and beta their expressions in terms of characteristic distances which we care about, we will get the final equation for the refraction, like forming image via refraction. We so far don't specify that we are some lens because lens will have two surfaces. So far we're dealing only with one surface, but that's enough already to form an image. So general equation for forming image with refraction will look like this: n1 over p, which is distance from the object to the interface, plus n2 over q, which is distance from the interface to the image, will be equal to n2 minus n1 divided by r. And r is the radius of the curvature of this interface between two optically transparent medium with different refractive indexes. So this is our equation for forming images via refraction in general. So let us summarize our discussion for today, where we introduced, first of all, focal distance as a parameter, important parameter for spherical mirrors, which is located at distance twice smaller than the center of the curvature. So if there are some light sources infinitely far away located from the mirror and rays are traveling parallel to the optical axis, then they will be collected in this focal position. Focal at the point, like focal point located as a focal distance. So
Besides reflection, there is another phenomena which can be used to form optical images. And that is refraction. So the principle is similar. We need also consider two rays in order to figure out where the location of the image will be. However, in this case, we know that we lose part of the incident light intensity because of reflection, and then we need to apply already this refraction equation in order to determine at which angle the incident ray will travel in the second medium. So in order to have this opportunity, we need an interface between optically transparent, both optically transparent materials with different refractive indexes. So we consider some specific case when incident angle θ1 is very small. So we simplify this refraction equation, and based on some geometry of this ray projection in two mediums, going through the interface with given curvature defined by radius r, we derive this equation for the image formation via refraction. So that's a general case. Later, we will consider specific cases. So simple specific case will be flat surface. So when we have just flat surface, means that the curvature, radius of the curvature approaches infinity. And obviously, our ultimate goal here will be to consider so-called thin lens. Most of real lenses are considered as thin lenses. And in that case, we will add one additional interface from the opposite side, which will also obviously influence on the image formation when light travels through both interfaces. So it will be air, glass, glass, air. And keep in mind, in this case, when we have a lens, we may have different radius of curvatures of these surfaces, and all these factors should be taken into account. So that will be our topic for next discussion. Now, thank you very much for your attention and have a good day.